The topic of today is a machine learning task which we can call decision support. My name is Johan Hagelbeck and I'm a senior lecturer at Linnaeus University. One of the earliest AI problems were decision support, and the first solution to this problem was expert systems. They often used a very large number of handcrafted if-then rules, and these problems are suitable for a type of algorithms called decision trees. So instead of handcrafting the rules, we can use an algorithm that learn rules instead, and a very effective type of algorithms are decision trees. And the dataset typically mostly contains categorical features, but it can have numerical features as well. So decision trees has one big advantage. The trained model is easy to visualize and interpret, so we can understand what the algorithm has learned, in contrast to some other algorithms that are more black box for us. This can be important in some applications where we want to investigate why the system took a decision, and this is commonly referred to as a completely transparent method. We can see what the method has learned. So as an example here, we will have the weather dataset, but where the numerical attributes temperature and humidity have been converted to categorical. So we have outlook, which can be sunny, overcast or rainy, temperature, hot, mild or cool, humidity, high, normal, windy, false or true, and the class label we want to predict is if we want to go out to play or no. So, taking this data set, we need to build a decision tree. And at each node, we need to find the attribute that best divides the data set into the categories yes and no. And to do this, we calculate what is called the information gain for each parameter and possible value. And the attribute with the highest information gain is selected at each node. And the information gained is calculated using the formulas below. But as always, it's easier if we step into an example right away. So we take the data set. The first step is to find the root node of a tree, which attribute and value should be in the root node. So we calculate the frequency of different values. So we have the outlook, which can be sunny, overcast and rainy, and in 2 cases outlook was sunny for examples with yes category. In 4 cases the outlook was overcast in the yes examples, and in 3 cases the outlook was rainy in yes examples. In 3 examples, outlook was sunny. In 3 of the no examples. In 0 no examples, we had outlook overcast, and in 2 no examples, we have outlook rainy. So we just put in these numbers into the formulas. So the information gain of sunny is 5 divided by 14. We have sunny has 5 in 5 of the possible examples out of 14. And we just put into the values, into the formula. 2 divided by 5, log 2, 2 divided by 5, we just take the numbers here. Sunny is 2 in the yes examples and 3 times in the no examples, and we have 5 examples where sunny is. So we just put into the numbers in the formulas, and the result is around 0.347. Overcast, we put into the values for overcast. We have 4 examples where outlook is overcast out of 14. And if we calculate the information gain, we see the information value is 0. And if we do the same thing by rainy, rainy has 5 examples out of 14. 3 examples belongs to yes, and 2 examples belongs to no. Just put into the values, and the result is 0.347. And the gain for Outlook is 1 minus the information gain for all the possible values, I sunny, I overcast, I rainy, and it ends up in a value of 0.306. So that's the information gain for the Outlook attribute. Now we need to find the information gain for the temperature attribute. And the temperature can be hot, mild, or cool, and we just calculate the frequencies of hot 2 times for yes examples, 2 times for no examples, 4 times is temperature mild in yes examples and 2 in no examples, and 3 times is temperature cool in yes examples and 1 in no examples. And we put into the values in the formulas. We have 4 examples of hot and 14 total examples. 2 of these are in the yes category and 2 is in no category. And the result value is 0.286. Mild, we have 6 examples out of 14 with mild, and 4 of those are in yes category and 2 is in no category. And the information is 0.394. And we do the same thing with cool, and when we take 1 minus all these values and we find the information gain for the temperature attribute to be 0.088. We do the same for humidity. Humidity only have 2 values, high and normal, and 3 times humidity is high for yes examples and 4 times humidity is high for no examples. 6 times humidity is normal for yes examples and once humidity is normal for no examples. We just put the values into our formula. High is in 7 out of 14 examples. 3 of those are in yes category, 4 is in no category, and the resulting value is 0.493. We do the same for normal and calculate the gain for humidity, which is 0.211. So just put the values into the formulas, not very complex. And the last attribute is windy, which can be true or false. And if windy is true, we have 3 examples in the yes and 3 in the no category. If windy is false, we have 6 examples in the yes category and 2 in the no category. We put these frequency values into our formula and calculate the information gain for windy, which is 1 minus 0.429 minus 0.464. Which results in a value of 0.107. And if we list all these information gain values in the table, it looks like this. The highest information gain is Outlook, 0.306. And since Outlook has the highest information gain, it is selected as the root node of our tree. So we start building the tree with Outlook. And Outlook can be sunny, overcast and rainy, and we can see that Outlook overcast has a perfect gain, meaning that all examples belongs to the same category yes. So in this case we can just say that the result if Outlook is overcast is yes. We classify all these examples as yes. And now we need to continue building the branches of a tree. The first branch is if Outlook is sunny, and we take a subset of the data were with all the examples where Outlook is sunny, and it's actually only 5 examples out of 14. And we take these 5 examples and put it into a frequency table. So temperature is the first attribute. We have already looked at the overcast attribute, so we can skip that. Now we need to look at the remaining attribute, which the first one is temperature. It can be hot, mild and cool, and we put into the frequencies here. Temperature hot is once in yes, 0 in yes and twice in the no category. Mild is 1 in each yes and no category. Cool is once in the yes category and 0 in the no category. And we can calculate the information gain. It's 0 in both because we have a perfect gain. And mild is 0.4. And we calculate the total gain for the temperature attribute, which is 0.6. The sunny node is the next is humidity for the sunny node, and humidity can be high and normal, and we'll see that we have a very good spread here. For humidity high, we have 0 in yes and 3 in no. For humidity normal, we have 2 in yes and 0 in no. So we have a perfect information gain of 1. You can double check if you put the values into the formula, but if we have a perfect separation, then the information gain will be 0 and the total information gain in this case will be 1. And the third is the windy attribute, which could be true or false. And if windy is true, we have 1 example in yes, 1 in no. If windy is false, we have 1 example in yes and 2 in no category. And if we calculate the total information gain, it ends up in 0.049. So we have 0.049, we have 1, and we have 0.6. But since the humidity node here has a perfect information gain, it is selected. So if outlook is sunny, we check the humidity. If humidity is high, all of these examples are classified as no. If humidity is normal, all these examples are classified as yes. And now we only need to find the rainy branch. If we take a subset of the data, we see that we have, in this case as well, 5 examples where outlook is rainy. 3 of these are yes and 2 of these are no. And now we need to find the information gain for the remaining attributes we've already done with outlook, so we need to look at temperature, humidity, and windy. For temperature, we have hot, mild, and cool possibilities. In the first case, we have 0 in both categories, so the information will then be 0. For the mild, we have 2 in the yes categories, 1 in the no category, leading to an information gain of 0.551. Cool is 1 in both, leading to a value of 0.4. And the total information gain is 0.049. Rainy node, or humidity attribute for a rainy node. Humidity can be high and normal, and we have a frequencies here, and if we calculate the information gain, the total information gain, we see that it's the same as in the previous temperature attribute, 0.049. And the third attribute is windy. And now we see that windy is actually a perfect separation. If windy is true, we have 0 in yes, 2 in no. If windy is false, we have 3 in yes and 0 in no. So windy has perfect gain, we select windy, and the remaining tree looks like this. So first we look at outlook. If outlook is overcast, when we classify the example as yes. If outlook is sunny, we look at humidity. If it's sunny and high humidity, we classify it as no. If outlook is sunny and normal humidity, we classify as yes. If outlook is rainy, we look at the windy attribute. If we have rainy and false, we classify as the example as yes. If we have rainy and true, we classify the example as no. The problem here is that in most cases there are several possible trees that can be generated, and the aim is to generate a tree that as accurately as possible can classify the training data. And we also want to generate the smallest possible tree. Sometimes it can be tricky to satisfy both, but of course high classification accuracy is of highest priority. And there's a wide range of different algorithms for generating decision trees. And each of these algorithms try to, as good as possible, fulfill both criteria. And Weka uses an algorithm called J48. In R, we usually use an algorithm called CART, but there are others as well. When we classify an example, we simply need to traverse the tree by following the nodes that matches the attribute values in the example, and when we reach a leaf node, the result of the category is returned. So it's quite simple to classify, and it's it's easy for us to see how the system came to its conclusion because we can just see where the classification traversed the tree. Decision trees can suffer from overfitting. It means that the model learned is very specific to the training data, but it can be bad at classifying unknown examples. And to get around this problem, learning is usually stopped before there is a risk of overfitting. The problem is to know when to actually stop learning. A common approach to reduce overfitting in decision trees is to stop creating more branches if there is only a very small increase in gain. So we can set up a minimum threshold of how large the gain must be to allow a new branch to be created, or how large the difference in gain must be. But there is no universal answer to which limit to use. You have to experiment on your own dataset. So, when shall we use decision trees? As mentioned, one big advantage of decision trees is that we can interpret the trained model. We can visualize how the model came to its conclusions. But there are also some other benefits of decision trees. They work on both numerical and nominal attributes without pre-processing the data, which many other algorithms don't. Instead of having a number categorized into categories like we did in this dataset, we can say that we can have a node that checks a limit of a number if temperature is above 25 or temperature is below 25 degrees. They also support probabilistic reasoning of assignments, which we did when we returned the most probable categories. So we can see which is the most probable category, but we can also see other possible categories that are least probable. The major drawback is that decision trees are not very good for complex learning problems. If we have a lot of categories, the decision trees tends to be very complicated and will most likely make poor predictions. Another disadvantage is that they can only do simple greater than or less than decisions for numerical attributes. We can't have any more complex mathematical functions. They work best if we have combinations of simple numerical attributes and nominal data and very few categories, which quite many real-world problems satisfy. The Weka Standard decision tree classifier is called J48. When using J48 on the weather dataset, we get the following result. Correctly classified instances 9 out of 14, only 64.2857%. So it's not a very good result. But this is when we use cross-validation, and cross-validation is quite sensitive if we have very small data sets with few examples. We can also use decision trees in R. In R we use an algorithm called CART, and in R the dataset needs to be in CSV format, comma-separated values. The ARF format is mostly used by Weka. I haven't seen any other library that actually use it. And the R script looks like this. First we need to load the machine learning library, which we call library, and caret is the name of the library. Second, we read the dataset. The dataset is variables called dataset, and we use a read.csv function for reading it, and we specify the file name. So as you see here, the way of writing code in R is a bit unconventional, but when we get used to it, it's fairly easy to understand. When we set up a tenfold cross-validation, the control variable is we use a train control. That's how we train the system. Method is cross-validation, and we have 10 folds. And the metric that we want to use is accuracy. And then we train the model using the CART. So we set a seed for the randomizer, and the CART model is trained using the player skill attribute in the dataset. and we specify that we want to use the variable dataset as data. Method rPart, that's what the carts algorithm is actually called here. The metric is accuracy, we already specified it, and we have the training control, that's we have also specified in the control variable, and in the end we print the result by using print cart. And when we do that, we get a warning. In nominal train workflow, there were missing values in the sample performance measure, and that's a common error if we have small data set. We'll look at it slightly soon. And we see that the result, the accuracy below, is only 0.55% or 55%, so it's quite bad result, a bit worse than Weka actually. The warning message from R means that the tenfold cross-validation split the dataset, so one class or possible class value was missing in some iteration. And this has large impact on the result. Weka get around this in some way. R needs, in this case, more data to accurately predict the dataset. If we make a copy of each example, so each example is presented twice in the dataset, so we have twice as much as data, we get a new result, and in this case we don't get the warning error. We have 48 examples here, and the result using it presents results using a bit of different parameter values, and the best result was 84.16667%. And that's slightly bit better than Weka, but I haven't tried Weka if we used the manipulated dataset where its example was presented twice. So that was all we had to say about decision support and the decision tree algorithm. Thanks.